So we are taking a look at graphing techniques in our Regents Chemistry curriculum, page 238 and page 239. So graphing, the reason we graph is it naturally organizes the data to help us identify a relationship, trend, or pattern among the variables. So our graphs will be based upon a plotted XY or coordinates, um, and which is the data we collected during the lab. So the x coordinate in graphing is referred to as the independent variable. So this variable is something that we set controls on or we manipulate during the lab experiment. In an ELA class, we might refer to it as the cause. Whereas the y coordinate, it is known as the dependent variable. And so this variable is impacted during the experiment. It's forced to change or react. And this is the variable we are studying and trying to learn more about. So in ELA class, we might refer to it as the effect. So the variable on the x-axis, independent or the cause. On the y, we refer to as the dependent and as the effect. So the cause and the effect. If a relationship exists between these two variables, the y coordinate will typically respond to the x coordinate in two possible ways. So the first possibility is if the variables react or change is directly proportional to each other. So that means as we see an increase in the x values, we will also see an increase in the y values. And as a result, when we look at our plot, we will always see a linear ascending line. And so we would describe the general trend. It fits as a best fit line. And when you look at our examples, when you look across the x-axis, it goes from 0 to 3 to 6 to 12. So left to right, we see the values are increasing. And when you take a look at the data points in order, we see that the x value tends to increase here. And once again, when you look at the y-axis, from the origin, we start at a lower number, 0, and as you move up the y-axis, we see the numbers increase. And when you look at the data points closest to the origin, and as they are plotted, we notice that there is also an increase in the y value. So this is a directly proportional set of data. So now, when it comes to this, we would have a best fit line. I do not have a ruler with me that I can use to help me draw this, but it's an ascending linear line. The line needs to fit within the data range. So we can't have any line out here, can't have any line out here. It is a straight line, so use a ruler, please. And it shows the general trend. So that means it may not touch every data point, including the first or the last, and it's really hard to draw with this. So I didn't do a very good job on there, but use a straight edge to draw that. Let me see if I can erase that. Okay, so let's see if I do shapes here. So here we go. Maybe I can, there we go. So now I'm getting a straight line. And when you take a look at that, it does not touch every data point perfectly. And notice there is no line stretching out beyond the data and no line below it. So the best fit line fits in there. And the purpose of that best fit line is not to represent individual data points, but it represents the best fit line, it represents, its job is to represent the general trend. Overall, we see an increase in the data points as the data is collected. The other type of graph that we might come up with is known as an inversely proportional. So as we see an increase in the x value, so take a look at the x-axis. So when we read each data point's x value, we see that it is increasing. But at the same time, when we look at those data points in the same order and read their numbers off of the y-axis, we see a decrease in the y value. So when we have this type of data, one variable increases and the other variable decreases, we end up with a data and it will create a more of a curved line. And so we refer to this as a best fit curve. When it's time to add the best fit curve to your data plot, okay, think of it as one smooth curve. I don't know if I can do it on the computer. See if I can draw this. So I'm not lifting it, not too bad, but once again, it may not touch every single data point, nor is it supposed to, but the purpose of the line is just to represent the overall general trend. If a data point like this one is pretty far off of the best fit line or the best fit curve, it probably means that that piece of data, compared to the others, has a little bit more error. So it deviates from the general trend a little bit. And that happens. So we're going to look at an example of creating a graph. When our graph is done and handed in, these are the things we should take into consideration. So if you're starting off with a blank sheet of graph paper, draw the XY axis, use a ruler. So they're nice, smooth, straight lines. Do not freehand so they're wobbly all over the place. Each axis, label it with the name of the variable and then in parentheses a unit. So maybe the variable that's being measured is mass, and the mass has been measured with the unit gram. So name of the variable, unit as an example. One of the things we're going to have to work on is the axis scaling. These numbers that we see on the axis, they must fit the data range. Okay, so the data range may not start at 0 or end at 100. We want the scaling to start just before and just end just after the data range. When it's time to plot the data points and circle. So make your data point and then circle it. Take a look at your data and determine if you need to put in your general trend line. Is it going to be best fit or the curve? So that line or curve, it just represents our general trend. So best fit because both are increasing, curve because one increases, the other decreases. So I'm going to put up, up because both increase, the curve, one increases, the other decreases. Okay? And then write a graph title, a simple sentence that summarizes the purpose of the plot. So now we're going to take a look at an example graph on the next page. So here we go. We are collecting data, temperature and volume information, about 50 grams of carbon dioxide trapped in a balloon, and it's being heated. So what happens to that carbon dioxide in the balloon? So we have our data, and now we have to graph it and plot it on the graph shown below. So some techniques to get this done. So first off, we need to know our X and Y axis. So if you are unfamiliar or can't remember, the x-axis, it runs across the paper, so it's the horizontal axis. If I can get my pen to work here. So this is x. And the y-axis, it is the one that rises up and it's vertical. So you might want to just label those. And according to the information that we're given, the data on the x-axis is going to be temperature, and it's been collected in Celsius. So right away, I'm going to name the variable and the unit. I'm going to go down and do that. So down here, I'm going to write temperature. And degrees Celsius. Whereas the y-axis information is volume, and the volume has been measured using the unit milliliter. So I'm going to take this information and try to write it here on the y-axis. So I've labeled my axes with the variable and the unit in which they have been measured. Now, we need to come up with number scaling a lot for the x-axis, and it has to fit the data range. So I have this little bit of information here to help us figure out how to know how much each line is worth. So we're going to take a look at the temperature. So the lowest temperature recorded is 21. So that means that my scaling on the x-axis needs to start just below 21. So I'm going to round it down a little bit. So I'm going to start my scaling at 20. Now the highest temperature recorded is 59. So that means that my scaling needs to go above 59, but 100 is way too far above 59. So I'm going to go for 60. It's a little bit higher than 59, and it ends in a 0. So now, next thing to get yourself set up so you don't make a silly mistake in the scaling is write the starting scale value. So this was where I'm going to start. The starting scale value on the x-axis is 20. So right away, I'm going to go down here and I'm going to write in 20. So I know I'm starting this scaling at 20. Now I'm going to use information to figure out how much each line is worth to the right of the 20. So next order, I've written in my starting value, count the number of lines remaining to the right. So here's my 20, how many lines to the right? And if you go through and count each individual line, you will see that there are 22 more lines to the right. Next thing is calculate the difference between where the scaling needs to start and stop. So that is those scaling values, 20 and 60. So 60 minus 20, so the difference is 40. So to determine how much each line is worth, I'm going to take the difference of 40 and I'm going to divide it by the number of lines I have to spread it through. And when I put this in my calculator, it comes out to 1.818181 repeating. So that means that the next line is 1.81818181 to infinity more, and then another 1.818181 to the infinity. That would be really hard to write down. So I am going to round this to a reasonable, easy number to work with. So 1.8, it easily rounds up to 2. So I'm going to make each line 2 more than the previous. So in our class, you need to either write in every value or every other value. And you work your way across. So I'm going up by 2s. So do you notice? Using that technique, I spread out my scaling. My data starts at 21, so it starts just inside the scaling. My data ends at 59, just before the end of the scaling. And take a look. The scaling spreads across the entire x-axis. And that is what we are striving for, to get it to move or use up most of the axis, because we want our data points as far apart from each other as possible. So now I'm going to do a similar procedures, but now for the y-axis data. So my y-axis is the volume. So now my lowest volume is 3. I can't start my scaling at 3. Starting it at 2 or 1, I could make it, but it makes it a little bit hard. So this would be reasonable to start my scaling at 0, because 0 is not too much less than 3. My greatest volume recorded is 37. So my scaling needs to end a little bit higher than 37. So I'm going to try to stretch it to 40, since those are easy numbers to work with. So next step, write this starting scaling value one line above the XY origin. So that means it's referring to this guy. That's where my scaling value is going to start on the y-axis. So I'm going to go down here and I'm going to put in a 0. So remember, I'm actually starting at 0. Now I need to count the number of lines remaining above that 0. So here's the 0. Now the lines above it, I need to count how many are there. And if you go and count carefully, hopefully you will count the same as me and determine or count that there's 14 more lines. So over these 14 lines, I have to figure out what I need to spread out. So that's the difference between where my scaling is going to start and end. So 40 minus 0. So that means my scaling has to cover 40 milliliters. So now I'm going to take my difference of 40 and I'm going to divide it by the 14 lines that are available. And when you put this in your calculator, you get a number that's 2.8571. That would be a pain in the butt to scale by. So I'm going to just round it to a number that's a little bit bigger, but easier to work with. So 2.85, it's reasonable to round it up to 3. So now I'm going to start at 0, and each line is going to be worth 3 more than the previous. And remember, I need to get just past 37, because my highest volume is 37, and I'm almost up at the top. And take a look. I'm ending at 39. So I have stretched my scaling out. Now the job is to actually put in your data points. So I have to find the data. So go ahead and take a minute here. So see how I can do this. So I'm plotting my data. It's not so easy to do it on a computer. I got 2 more data points. 6 and 31. And 59 and 37. So now I have to figure out if it's a best fit line or a best fit curve, depending on what's going with the data. So when I take a look at the X values and compare it to the scaling, So when I look at it left to right, I notice that there's an increase in the X value. Looking at the data points in the same order and comparing what happens to their Y values, looking at the same order, I notice as the X values increase, the Y also shows that they are increasing. So this is a best fit line, meaning that the data shows a direct relationship. So this means I need to get out a ruler and use a straight edge. Now notice when you look at this, you can see that these 4 data points really show that relationship. And the first data point and the third one are a little bit off. So take a look at how I'm going to do this. So I'm going to start my best fit line here, and I'm going to carry it, make it linear and straight, and I'm going to end it there. For whatever reason, this first data point and this third data point throw the trend off a little bit because they have a little bit more error, and that's okay. So it's not on there because it contains more error. I didn't read the instrument correctly. I didn't read it at the correct time frame. There's a variety of reasons. Now, the last thing we need to do here is to write a title. We're going to keep it simple. So I'm going to take a look at what is happening with my independent variable, the temperature. So when I look left to right, I'm going to write a sentence. So as the temperature, and I'm going to identify what is the material of the CO2 gas, and I know it's CO2 gas because it tells me that at the very top of the paper. So as the temperature of the CO2 gas, we notice it is increasing. The CO2 gas increases. We always write the title based on the data plots, how it falls on the graph. So the CO2 temperature is increasing. So as the temperature of the CO2 gas increases, now I'm going to talk about the other variable, the y-axis variable, the volume of the CO2 gas, and we said it was also increasing. So the volume of the CO2 gas increases. So we're going to keep it nice and simple.